So I want to talk a little bit about prime factor trees. So before I do that, I want to talk about what a prime number is, so we can talk about what a prime factorization is. So you might recall that a prime number is, most people think of it as any number that's divisible by only 1 in itself. And that's almost correct. We want to be careful that we're only looking for numbers that are larger than 1. So a prime number is any number larger than 1 that's only divisible by 1 in itself. So some examples of prime numbers would be 2, 3. Now 4 is not a prime number because it's also divisible by 2. 5 is prime. 6 is divisible by 2 and 3. 7. 8 is divisible by 2 and 4. 9 is divisible by 3. 10 is divisible by 2 and 5. So we get up to 11. 12 is not prime, but 13 is. 14, 15, 16 are not prime, but 17 and 19 and 23 are, and so on. Now, so the goal here will be to represent any number as a product of prime numbers, so that you can write any number as by multiplying together its prime factors. So an example of that would be, a very easy example would be that 10, well, what prime numbers do I have to multiply together to get 10? I would have to multiply 2 times 5. If I want to do a slightly more interesting example, I could do 24. Well, that would be 2 times 2 times 2 times 3. It's 2 times 2. It's 8 times 3, but 8's not prime, so I have to break up the 8 part into 2 times 4. But 4 is not prime either. That's equal to 2 times 2. So I can get 2, 2, 2, and then a 3. If I multiply all 4 of those prime numbers together, I'll get 24. And that's a statement that could be made in general. Any number bigger than 1, any whole number bigger than 1, you can break up into a product of prime factors in one way and only one way, assuming you're willing to reorder your prime factors. So what I mean by that is 10, if I try to break it down into prime numbers, the only way I can do it is 2 times 5. I could write 5 times 2 if I want, but really I haven't changed anything. Same thing here, 24. If I try to break it down into its factors, I could have, instead of done 8 times 3, I could have done 4 times 6, but that'll get me to the same place. The 4 splits as 2 times 2, and the 6 splits as 2 times 3, and I still end up with 3 2's and a 3. And I could write that in any order. I could put the 3 in the front or the end or in the middle somewhere, but one way or another I still have 3 2's and a 3, and that's what 24 is. If I multiply 3 2's and a 3, all you can get is 24. So this is a method of bookkeeping that's useful for computing these prime factorizations to find the prime numbers that are that make up the factorization. And so if I look at the number 75, well, I can tell pretty easily by looking at it that it's divisible by 5. And so I'm going to split the 75 into 2 parts. The first part is going to be a 5, and then I'm going to divide this 75 by 5. So 5 goes into 75 once, with 2 left over, and then it's going to go into 25 5 times. So 75 is equal to 15 times 5. And so when I split it, I'm saying that these two numbers multiply together to give the one above it. And so then within each branch, if my branch ends in a prime number, then we stop that branch. So I've ended with a 5 here. 5 is prime, but 15 is not, so I'm going to keep going on the 15 branch. So I split the 15 as 3 times 5. Now 3 is prime, so that branch is done, and 5 is prime, so that branch is done. So we see that 75 is equal to 3 times 5 times 5. And again, if I had split 75 some other way, like I might have noticed that 75 is 3 times 25, that's fine, but then I just split the 25 as 5 times 5, and I end up in the same spot with 3 times 5 times 5.